an introduction plan, but after that, I think I'm just going to scrap it because I couldn't have done that good about myself anyways. But so, like Mr. Miller said, I'm going to teach you guys, it's a Cal 4 technique. It's referred to as triple integration. Now, it might sound scary. It's really not that bad. It's basically finding volume of, Mr. Miller, may I please borrow one of your expensive visual aids? Sure. Okay, sweet. Oh, nice. Okay. Yeah, so in college algebra, you find the volume of items like a circle or a square, cubes, cylinders, things like that are just perfect shapes that don't have any ridges or form to it. It's just a nice little perfect shape. Well, in calculus, we find the volume of stuff like this that has all these different ridges inside of it and holes and, you know, gaps in between each row that you know, you have to account for and things like that. So that's what I'm going to teach you how to do, is find the area and of things like, or the volume of things like this. So to start off, in math in general, everything that you've learned up to this point is either in terms of, well, did they get to that far? Mm-hmm. X and Y? Mm-hmm. Okay, yeah. Okay, yeah. So you have functions such as f of x, and this is, well, like y'all know, is equal to y. So you may have a function f of x is equal to x squared plus 3x plus 2. Okay. So this is how functions have been up to this point. Well, now in Cal 4, we learn functions that are in terms of x and y. And you may have variables mixed in together like 2xy plus 3x squared y cubed. And f at xy is also the equivalence of z. So not only do you have height and width, but you have to the wall and in your face. So it gives things depth in a way that we haven't examined before. So it works the same. We solve these equations the same exact way you would solve a regular equation. Alright, so multiple integration. Integration is this symbol right here. It is basically an adding machine. That's all it does. Archimedes, if I'm not correct, was the guy that came up with integration. And his idea behind integration was that you have a curve on a graph, and just some random curve here. And he used the idea of rectangles to find the curve, because he knew how to find the area of a rectangle. And so in order to do that, he would draw little rectangles in here that would blank this off. That would blank this off in order to calculate the area of these curves. And if you can notice, every time you draw the lines or whatever, there's always a gap, because he would build off of them. So he could never quite exactly calculate the perfect area because there's always little holes in there. So in order to do that, he developed this technique called integration. And what integration does is it takes together all the area of one curve to a certain point and the area of the other curve at a certain point, and subtracts them or adds them together depending on the situation. So an example of an integration problem would be something like this, or a single integration problem would be something like this. Say you have some function 2x dx. Okay. Well, this dx is what determines what action the variable gets. You have to perform different math techniques on these. One of the most common techniques is what Mr. Miller refers to as add 1, divide by. You take the integration and other calculus-based things always deal with exponents. So since this has an exponent of 1, that looks terrible. Exponent of 1. You would just add 1 to the exponent, so it would be integration of 2x squared, and then you divide by the exponent, so you have 2. So the 2's will cancel, and you just have x squared. And that's how you solve just your basic integration problems. And doing double and or triple integrals is the same thing, except you have a little bit more of a form to follow. You have things like, for example, a double integration problem. You would have xy dx dy. Okay. In this problem, variables, this is going to sound really strange, but it sounded really strange to me too, but in calculus you learn up until Cal 3 that variables are variables and you can't touch them. But in Cal 4, everything changes, everything's backwards. Variables become constants, and you can get rid of them, and you can add them in at certain times, and it gets really confusing, but it's not that bad. So in this problem,